All right, so now that we've gotten through our kind of definitions of our acids and bases and some examples and mechanisms, um, one of the big questions that's going to come up is how do we know if something's going to be an acid or a base if it has both some lone pairs and a H that can be abstracted as a proton? And one of our kind of major kind of like values that we'll use to make that comparison a lot is going to be a value called pKa. So pKa is expression kind of like pH. pH, you're going to take you're going to look at the amount of either like your hydronium, and then you're going to run it through a log, and that's going to be how you kind of get your pH value. pKa is kind of similar, where because of the fact that there's a lowercase p, you're going to run something through a log. What you run through the log for your pKa is going to be your Ka. So that's kind of like what your H is, and your pH here is going to be Ka. And Ka is a equilibrium constant that comes from actually looking at the actual like reaction itself. You can do a bunch of math. We'll say that's outside the kind of purview of our class. And here we're just going to primarily just use kind of like pKa's from like general trends and on tables and stuff. And in the Moodle, there's actually like 3 sets of handouts that have a bunch of different structures and functional groups and things of that sort, and what their pKa values are. So kind of like for our kind of like thought process, we can generally think of pKa, and for pKa, a lowercase p, a capital K, and then a lowercase a or a subscript a. Doing subscripts is hard, so we'll often try to as a lowercase a rather than a subscript a. But pKa is going to be a measure of how hard it is to remove or abstract a proton from our molecule. So, and then kind of generally, higher numbers means harder. So a really, really high pKa means it's really hard to remove that proton, meaning it sucks as an acid because you're not able to take off that H really well. So your strong acids are going to be structures that are going to have a Ka greater than 1, which is actually going to give you a negative pKa. You don't want to think about greater than or less than signs. pKa less than 0, which means negative. Where weak acids are going to be values that will have a positive pKa. Almost all of organic molecules is going to kind of sit in this kind of range of your weak acids. Almost all of them will have a positive pKa, which means that they'll be weaker acids, but still acids. So there's a bunch of different, oh, I just shifted that. Get that back. There are a bunch of different tables and stuff in Moodle that have a bunch of different pKa values. Here's just kind of like some of the most common ones that you'll see. So pKa of your hydronium, which is going to be kind of like our original acid that we were talking about back in Gen Chem, has a pKa of -2, meaning that's going to be really easy to remove that proton. Anything that's going to have a positive charge is generally going to be a lot more acidic because when you remove that proton, it gets back down to a neutral. For organic chemistry, one of the most common functional groups that we're going to see is going to be a carboxylic acid, and that's the second one here. As the name carboxylic acid suggests, it's generally going to be an acid. And the one thing that I'm going to tell you again and again and again is that the pKa of a carboxylic acid is around 5. That's kind of like one of our benchmarks. I have, and we'll talk about it in a little bit, pKa of around water is around 16. 15.7 to be super exact, but our alcohols are generally that 15 to 16 range. Here, I'll actually do it in black so it looks like it was originally there. 15.7 to be super specific. If you look at a phenol, which is going to be an alcohol directly attached to a benzene ring, that has a pKa of around 10, which is around the same as your ammonium ion. That's our NH4+. Water is around 15.7. Simple alcohols, so like for example, like methanol, 15 to kind of 16 range. A triple bond, which is your alkyne, has pKa around like 25. Any just CH stuff and double bond stuff is way higher, is way up in like the 45 to 50 range. And then some of like our nitrogen stuff. So this is our nitrogen. This is triethylamine, is up around like 35. These are just kind of like some relative values of kind of like things that you can kind of like think about. Now, often we're going to be kind of comparing stuff to water, and water is a decent solvent. It kind of exists everywhere, and generally, like if you have a pKa that is going to be lower than that of water, water is going to be the base, and then you're going to be an acid. If you have a pKa that's going to be higher than water, then water is probably going to be the acid, and then you're going to be the base. So kind of like that kind of benchmark around 16 will kind of give you like a decent hint to whether or not you'll kind of like be an acid or base in most cases. Way back when we were thinking about like our very first example, we were talking about some nitrogen stuff, and a lot of our nitrogen stuff has pKa's up in like the 30s, and you'll see that's going to be higher than water. It's going to be doubled, plus a little. So because of the fact that pKa is so high, that means that that proton that you'd have on that nitrogen wouldn't want to fall off super easily, and that's why we actually see them being bases more than acids. Now, I do not want you to go through and just memorize a bunch of pKa values. I'm actually going to pause for a quick second and kind of show you where they are in the Moodle, just so you can kind of see where those tables are. Whoa, now we're in the Moodle page. So under Moodle, if we go to our acid-base unit, if you scroll down to like the extra documents and review sheets, there's pKa chart 1, 2, and 3. Each of these are going to be PDFs that will have like a bunch of like kind of like common structures. These were all ones that were made by other people to kind of show kind of like some relative strength of a bunch of different organic compounds and things of that sort. Those are just kind of like for like general reference. Now, with these, I don't actually want you to go through and just memorize or know a bunch of these different pKa values, because the focus of our next set of videos is going to be thinking about kind of a little bit more comparative, where if I look at two different structures, can I focus on what is that overall structure, and thinking about some general trends, and you can actually predict your relative strength and rank different molecules without having to actually go through and like look at a pKa value. And that's going to be the entire focus of our next video. But in general, when we're thinking of pKa, it's kind of a measure of how easy or hard it is to pull off a proton from it. And I think we'll go and stop there, and then our next one will focus on thinking about some general trends with acid strength.